Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode problem number 2577. Minimum time to visit a cell in a grid. This question has been asked in Atlassian and Google. And it is based out of graph theory, just another variation of finding the shortest path. Here is the problem statement. In this problem, we will be given a grid of size m cross n of non-negative integers and grid row column. It means the grid value is going to represent the minimum time required to be able to visit that current cell. What is the minimum time? It means we are starting from 0, 0, and when we are reaching at this cell, the time should be greater than equal to 1. Initially we are starting at 0, 0, and after every move our time will increase by 1 second, and these are the 4 directions where we can go. Return the minimum time required in which you can visit the bottom right cell of the matrix. If it is not possible, return -1. Let me conclude the problem statement for you. We are given m cross n grid of non-negative integer. And what is the value in that grid? Value will be the minimum time required to be able to visit that cell, that particular cell, row column. Okay. And we are starting our journey from 0, 0. And we have to reach m-1, n-1. During that journey, find the minimum time required to be able to visit the right bottom cell. If it is not possible, then return -1. Let's have a look on the grid. Here we have to start our journey from 0, 0, and we have to reach m-1, n-1. And we can move in any of these up, down, right, left position. But when we are moving to a particular cell, the time should be greater than equal to the grid value. It means that when we are starting here, it should definitely be 0. Okay. When we are coming here, the time should be greater than equal to 1. 0 to 5 we cannot come because when we are coming to 5, our time is 1. But 1 is not greater than equal to 5. This condition is not fulfilling. It means this path is not valid. From 0, in this case or in this example, we have only one possibility, that from 0, 0, I can go to 0, 1, which is this one. When we are coming to 1, my current time is 1 and 1 is greater than equal to 1. So it is a valid path. Now you may wonder, let's say what we have 4 instead of this one. Here I have updated the time. Now we are starting from 0, 0 and we have two possibilities. Either we can go to here or here, but we will be able to go if my time is greater than equal to the grid value at that particular row and column. In this case, it is at row column 0, 0, 1, it is 4. And my time is 1. 1 is not greater than equal to 4. So it is not a valid path. Similar to this case, it is not a valid path. If there is no valid path from initial position, then how we can expect further? There is no valid path from 0, 0. It means it is impossible to reach to right bottom. This thing you have to keep in mind. But let's say when we are at middle position somewhere, I have further updated the example and now this time the 4 is at this position, this cell. Now from this starting position, we will be able to come to this position because 1 is the time and greater than equal to 1 is the condition that is fulfilling. Here we cannot go, so this path is not valid. There is only one path. From 1, we will try to explore the possibility. 0, we will not go because it's already, we are coming from there, that location. Or we'll see later on. From 1, we have to reach any of the forwarding location. If I come from 1 to 3, it means I am coming from 0, 1 to 0, 2. Coming from 0, 1 to 0, 2 is when I reach 0, 2, my time will be 2, 1 plus 1. At 0, 1, my time was 1. My time is 2 and I will check whether 2 is greater than equal to 3. That is not possible. It means we cannot go to 3. And when we are coming down from 0, 1 to 1, 1. At 1, 1, the time will be 2. 2 will be matched to 4. This is also not possible. This is also not possible. Does it mean that we cannot go to these cells? No. Here there is one catch, that we can only go to any of these cells when the time is greater than equal to 3. And now currently the time is 1. Can we increase this time? Yes. If we are at this position, it means we have definitely come from a previous position. So move back to that previous position and come back again. So the time will be increased by 2 units. When I checked on the initial position, there is no previous one. We have to make the first move. But when we are not at the initial position, we are at this position. It means we definitely came from any previous position, and we can utilize that position to be able to increase our time. My current time is 1. So, and I am at 0,1. So if from 0,1, if I go back again to 0,0, from time 1, it will become time 2. And then again, if I try to come to 0,1, it will be time equal to 3. So I'll just make one move. So from 0, 0, I'm coming to 1. From 1, I'm again coming back to 0. Then again come back from 0 to 1. And this time, the time is 3. And now we can move to the next position. Let's say instead of 3, it is 34 on the right side and 41 on the left bottom side. Can we increase time to that extent? Yes, we can do that. Every grid value is going to be non-negative integer, and we can increase the time by doing the to and fro motion from the previous location. It means that only when we are at the initial position, we have to see, can we go to any of the direction? If we are able to go to any of the direction, we will definitely be able to go to each cell. Just that we have to increase some time. So I came from t equal to 1 to t equal to 3, and when I am at 3, I will be able to jump to this position. So whenever my t is not sufficient, I will be able to add. So whenever my t is not sufficient, I will be able to add k quantity of 2. Like if I do one motion, go to the previous node and come back again, plus 2 will be added. And then going back and come back again, plus 2 will be added. Let's say my time was 1 and I require 3 time. It means the wait time is 3 minus 1, which is 2. 2 is my wait time. It means somehow I have to pass the time. 2 is a multiple of 2, so that is possible. If I go back and come again, it will be equal to 3. But let's say if I require t equal to 4. In that case, I have to be able to do the weighting of 4 minus 1, weighting of 3 unit of time. So if I come back and go to the previous node and come back again, the time is currently 3, but 3 is not fulfilling. I will check 3 greater than equal to 4. It is false. So I will again do the one operation. I will again go back and come again. So from 1 to 3 and 3 to 5 it became. Now at 5 is greater than equal to 4. It is valid one. So now I will take a jump to the next node. Okay. In that case, what I realize is that wait time is a multiple of 2. Then we'll just have to we'll be able to successfully make the operation. When the wait time is odd number, I need to adjust the time somehow. When my time is some value and I have to do some kind of wait operation. Waiting time, how do I find? The current node value, let's say in the graph, the current node value minus the current time from the node we are trying to come. Okay. Now we have the wait time. We will see if the wait time is even, we can utilize that wait time. Our time will be incremented by that wait time. Let's say the wait time was 2. So from 1, I was able to reach to 3. Let's say the wait time is 3. It means we have to reach to 4. But we cannot reach 4 from 1 because every operation we are adding 2 unit of time. So in that case, I need to make one adjustment, that plus wait time plus 1 when the wait time is odd. Okay, so this is something tricky that we have to add in it. Otherwise, it is just a Dijkstra algorithm. We can utilize Dijkstra algorithm to find the minimum cost path. And whenever we are coming from any node, let's say we are coming from 0 to 1, I will keep on mark that node visited. I don't have to actually come back to the node. I will just calculate the wait time, and according to the nature of the wait time, whether it is even, I will just add those number of 2's in my current time. If it is even, I will just adjust the time by adding one extra one to my time. Yeah, I just have to do this adjustment, and this adjustment is a constant time operation. Let's also have a look on the time complexity of this program. Here my grid if is of size m cross n, and we are going to utilize the same time complexity as of Dijkstra algorithm, which is the number of element and the insertion into the priority queue. Insertion into the priority queue is a log operation, so it will become m into n into my log m into n. So this is going to be my time complexity. And what is the space complexity? Complexity is going to be m into n for my priority queue. Now let's code this problem. So here it is clear that we are going to use the Dijkstra algorithm with some modification in it. First of all, we need to see when my solution is not possible. If on the neighboring node of my starting node is greater than or equal to 1, then my solution is not possible. Why? Because we cannot adjust the time in that case. 0, 1 and 1, 0 are the neighboring node of the starting node. If any of the time is greater than 1, then the solution is not possible. Otherwise, the solution is definitely possible. Let me initialize a couple of variables required for my approach. I will have direction array to navigate in the grid and the boolean visited array to be able to keep track of the visited nodes. Here we are moving to the previously visited node to adjust the time, but we are not actually going back to that move. It's just a constant time operation, just calculating the wait time. If the wait time is even or odd, I will just process what will be my actual time. Here we have taken the visited array, and we actually are not going to the previous node to adjust the time. We just use a constant time operation as per the wait time value, whether it's even or odd. Let me initialize m and n. M is the rows and n is the number of column. Now I will initialize a priority queue for my Dijkstra algorithm approach. Priority queue will be of integer array pq is equal to new priority queue. And what will be the logic here? In this array, I'm going to store the cell position, which is row comma column, and the time so far. So time is at second index. I will be comparing as per I will be maintaining order as per the time. So A2 minus B2. Boolean array is going to be the same size. Visited array is also going to be the same size, m cross n. And initially in my priority queue, I'm going to have 0, 0 from my starting position, and the time is also 0 initially. Now while the priority queue is not empty, firstly I will poll the current element, priority queue dot poll. What is the row value? Current value 0 is the row, and column is current 1, and the time is current 2. This element we are going to process. First of all, we will see whether we have reached the destination or not. If we have reached the destination, this time is going to be my answer. Row equal to m minus 1 and column equal to n minus 1. In that case, we just have to return time. Otherwise, we will move to the next node. Now we will check if the node is visited or not. If row column is equal to true, if it is visited, just continue. Otherwise, mark it visited and do the processing. For processing, we'll move to every single direction for integer array d for the direction. And what is my updated row? Updated row is going to be row plus d of 0, and updated column is going to be column plus d of 1. I will see if it is not valid. If it is not valid, I can continue in that case. Let's write our valid helper function, integer I will return true if it is a valid index. And now in the end, as this is a valid cell, this definitely going to be added to my priority queue. New integer value. What is my new row? Is R, new column is C, and new time is T. Here T is my updated time. And what is the value of time? In normal cases, it is going to be equal to 1 unit. But sometimes when we have to do some kind of waiting operation, we will do to and fro motion and adjust the time. So let's take another variable. In T is going to be equal to math.max. Either it is equal to my time from previous entry plus 1, or it is equal to grid, row and column. But there is also possibility when we have to adjust the time and we are coming with one extra time, because whenever we are adjusting, we are adding 2 to my time, this time variable. So to adjust that, I also need to see, let's call it a variable f factor is equal to grid, row, column minus time. If this value is, this is my wait time. If this value is even, let's say it is 2, wait time is 2. Now if you have a look on this example, from 0 0 when I'm coming to 0 1, now the time is 1 and I have to go to 3. 1 is not greater than equal to 3, so I will make the time adjustment. I will go back, time has become 2, now I'm coming back, time has become 3, now it is 3, and now if I go to this position, my final time will be 4. So whenever the wait time is even, I need to make one adjustment. So if grid rc minus time divided by 2 modulus 2 equal to 0, in that case I will add another 1 to my time, wait time, not one factor. Okay, so this is the adjustment that we have to make in this algorithm, otherwise it is same as the Dijkstra algorithm. Let's see if it is working fine on sample test cases or not. On sample test cases it is working fine. I'm submitting the problem. Submitted successfully. I hope you have understood the problem. If you have any doubt, you can comment down below. I will try to address your questions. And as a summary, what we did here is we just used the Dijkstra algorithm and did this time adjustment. So that is the only tricky part which is making it hard. Okay guys, bye bye.